This should be a short segment in which we talk a little bit about catalysis. A catalyst is something, it's a substance, as it says there in the quotes from the glossary. It's a substance that can increase the rate of a chemical reaction without actually being a reactant or a product. Okay, these are very, very common in industrial chemistry. They're also very common in biological chemistry. Your body is full of biological catalysts for various processes. Enzymes are the classic example of that, of a category of substances that act to catalyze important reactions that take place in living things. Okay. In chemical industry, catalysts are very often metal surfaces. We'll take a little bit of a look at the end of this segment at the details of how such a process can work and why the surface of a metal can sometimes speed up a chemical reaction. So how does a catalyst get to speed up the reaction if it's not one of the reactants, it's not one of the products, it doesn't show up in the actual rate law? Okay, it has to be something kinetic, right? Because we're still getting the same reactants and products. And so the reactants and products, what those are, that's kind of the realm of thermodynamics, right? Where everything was about delta E, delta H, just the difference between the products and reactants in various quantities, okay? Catalysis works by having the catalyst somehow make the reaction have a little bit easier pathway available. What does that mean? It means in terms of the activation energy that we've just talked about, it means that the catalyzed reaction, the reaction in the presence of the catalyst, will have a lower activation energy. Okay, that'll make the rate constant be higher, make the reaction go faster. The catalyst doesn't change things about thermodynamics, which is the position of equilibrium or how much product you get in the end, right? It can't do that. It can't shift what the distribution of products and reactants is going to be, but it can get you there faster, right? All the things that we get from thermodynamics are all about what is the eventual outcome without any reference to time, right? And catalysis, or kinetics rather, is the part where we actually think about the time involved. And that's kind of how this is going to work. So let's take a visual look at how a catalyzed reaction might differ from an uncatalyzed reaction. This is just a comparison of a pair of these potential energy curves, right? So the y-axis is energy, the x-axis here, this is like two side-by-side graphs, basically. The x-axis would again be this reaction coordinate or progressive reaction, right? So for example, over here, this is the reactant energy, right? This is the reactant energy, and down here, this is the product energy, right? So this reaction that we're talking about is exothermic because the products are lower in energy than the reactants, right? The blue path is, say, the reaction if there's not a catalyst present, right? The activation energy is whatever is the length of that red arrow up to the top of the blue mountain, okay? On the green plot on the right, we have the reaction in the presence of the catalyst, and you can see that the red arrow is shorter. The height at the top of the activation barrier up to here versus here, right? My activation energy has been decreased by quite a bit. So this says the reaction with the catalyst, the version on the right, should be a lot faster, right? Because remember that Arrhenius equation, the expression for the rate constant has e to the minus e sub a over RT, right? And so if E sub A gets smaller, that'll make the rate constant K get bigger, right? So this will speed up our reaction. Notice the reactant and product energies are still in the same place on both of those plots, right? Because that we can't change. That's just what are the reactants, what are the products. Right? So the only thing that's changed is the part in the middle, which says the catalyst has somehow changed the mechanism of the reaction. That's one way of describing this, right? It's opened up some alternative pathway that says we no longer have to climb over the top of that large mountain. We've got some other route to go, in some sense, around it, or around part of it, so that the activation energy is lowered. Okay, and that's what a catalyst does. I'm going to talk just as an example to pick something. This is an example that is one of the reactions that takes place in the so-called catalytic converter in the exhaust system of a car. Right? It's the oxidation of carbon monoxide, CO, to make CO2. Right? That happens in the car exhaust system because we don't want carbon monoxide being emitted. Carbon monoxide is toxic, and so we want to try and get rid of as much of that as possible from the exhaust stream before it comes out of the car. There's a new symbol for a state of matter here, this one that says add, and add is what that really wants to say there. That would mean adsorbed. And adsorbed is a word that you probably haven't seen before. Absorbed, the more normal word, means something soaks into, right? So if you you spill some water, you blot it up with a towel, you can say the towel is absorbing the water, right? Adsorbed means it's sitting on the surface. Okay, it's a word that's pretty specific to surface chemistry, at least in my knowledge. Okay, so what does this say? It says I have my platinum surface, and in this case, I've drawn the little sketch here as if the platinum surface is just like a sheet of platinum or a wafer of platinum. Okay, that would be a very expensive way to do this, and that's not what really happens in the car exhaust system. But it's an easier one to picture, okay? Carbon monoxide will stick to the platinum surface, and so the right-hand side of the top equation says CO add, meaning adsorbed, which means there's a bit of a bond here. Sorry, I'm trying to do this with the mouse, and it's really not working. There's a bit of a bond there holding my carbon end down onto the platinum surface, right? And there are tools that tell us that we know, for example, that molecule stands up, carbon down, and oxygen up at something close to a right angle, okay? The key to how this reaction gets sped up enormously by the catalysis is the oxygen part. When an oxygen molecule encounters that platinum surface, it makes a pair of bonds between the oxygen atoms and the surface, right? So these both get attached, but those together, that releases enough energy to make up for the fact that it can actually then tear the O2 molecule apart. Right. The reason why this reaction, which would just be CO plus, say, CO plus 1/2 O2 makes CO2, that would be the overall reaction, right? That's slow if they're all gases, just because it's hard to break those two oxygen atoms apart, right? They want to stay bound together. The oxygen-oxygen double bond is pretty strong. In the presence of the platinum, the bonding is different, and it's able to actually pull those two things apart. Once I'm in that middle picture on the bottom, those things are bound to the surface, but it's a little bit like they're a two-dimensional gas. They'd be able to sort of skate around on the surface, hop from site to site. Okay, but what will happen is if one of these oxygen atoms were to slide itself up near the carbon, then those things can make a bond. It forms CO2, the product, and the other thing that's important to how this catalyst works is that CO2 does not actually stick to the platinum. So as soon as the CO2 molecule is formed, it takes off back into the gas phase. Why is that important? Because that means our surface does not just get covered up with CO2. Right. So every time one of those CO2s leaves, there's room for more molecules to come and bind themselves to the platinum. That means I can have that same platinum surface in there, and it can continue to catalyze the reaction over and over again because it's not actually getting used up. It's not getting covered up in any way. Okay. So that's how the reaction works on the surface. There's actually a lot of experimental tools that let us know things, like when I say I know that the CO molecule stands up and I know that the oxygen atoms get separated apart from one another. There are experimental tools that let us see all of those things. I actually used to do surface chemistry in the past, and so this is one of the topics I actually know somewhat more about than other things that we sometimes talk about. So a little bit more about this reaction, just because it's a sort of a practical application, and people that want to go into engineering are usually sort of practical people. And so the actual catalytic converter in a car does a few things. It removes carbon monoxide. It removes things that are generally referred to collectively as NOx, which just refers to various oxides of nitrogen. Okay. The catalysts in there are actually a mix of platinum and rhodium metal. Platinum and rhodium happen to be two very expensive metals. They're relatively scarce, and the places where most of them are mined are not the easiest to get things out of, okay? And so that is unfortunate, right? There's lots of folks working for car companies constantly trying to devise a way to do these same reactions without having such an expensive metal in there, right? A long time ago, I remember, none of you can remember the sort of advent of what is officially known as unleaded gas, and that happened at the same time that these catalytic converters actually started to get required in exhaust systems, and that was because the lead content in older gasoline would have fouled the catalyst. It would have just gotten a film of other things sitting there that would stop the reactions from happening. Because those platinum and rhodium metals are expensive, you don't actually just use a platinum a chunk of platinum or anything like that, because what's happening? The molecules are sitting on the surface of the platinum, say, right? And that means the more platinum surface atoms we have, the better it is, right? And so the way to do that is to take your metal and sort of grind it up into a powder. If you have a powder, then almost a lot more of the atoms are at the surface, right? For the same mass, you get a lot more surface area in a powder than you do in a just a block, right? Imagine if you had if you had a sphere of a certain mass, that would be the minimum surface area that mass of say platinum could have. But if you took that same amount of platinum and just divided it up into little chunks, you'd get a lot more of the atoms sitting at the surface, right? And so the way people actually engineer the real catalyst is to take the metals, grind them up into a powder, and then that powder gets deposited on what are usually like the sort of porous ceramic materials, which just let you disperse those metal particles so that the gas can still get at them, okay? In doing that, you make it so that a large fraction of the platinum atoms are actually exposed on the surface and can therefore be doing the catalysis, as opposed to having a bunch of atoms down in the bulk of the metal, which really aren't doing any good, right? Because the gas molecules are not burning themselves into the solid. They're just sitting on the top layer, basically just perched on top of one of the metal atoms in that piece of solid. That's just a quick little bit about catalysts and how they work. It's not something that we're honestly going to ask you a lot of questions about or anything like that, but it is something that is kind of a practical application of chemistry, something that's actually really important in the chemical industry, because any reaction, if you can develop a catalyst for a reaction, you can do the reaction faster. And if you're in the business of making product and trying to sell it, then being able to make it faster is almost always a good thing, right? So lots of industrial concerns spend a lot of time and effort researching, trying to find better catalysts. In the auto industry, for example, if you could devise a way to carry out these reactions, and instead of using platinum and rhodium metal, you could use something like, I don't know, ground up old beer cans, then you would get to be a very rich person, right? Because you would be reducing the cost of that catalytic converter by a large fraction of its current costs.